Listen, do you smell something? Look at my application of Gauss law to find an electric field. And I am using a surface of a spherical insulator, which is represented in my diagram right here. Given that the charge is uniformly distributed in my pluses, and it's Q enclosed with the radius of R of the sphere and the volume charge density, which is basically the charge over the volume, is rho. We're going to find the electric field E at a certain radius, either inside or outside of the sphere. And we're going to write it in terms of rho. So the Gauss law states that the electric flux is how much field is passed through an area. So it's just the closed integral of electric field times the change in area. Or because we have all the constants, Q, R, and rho, we can just write it as electric field times area. We also know that it's going to be the charge enclosed over the epsilon. So using this formula, we're going to find electric field inside and outside of the sphere, which is different. So when little r is smaller than our radius, we are going to have electric field times area, which we write in terms of 4 pi r squared. This is a little r, because that's the area of a sphere. And the charge enclosed, we rewrite in terms of rho and volume. So it's just rho times 4 over 3 pi r cubed, which is the volume of a sphere, divided by epsilon naught from this equation. Simplifying 4 pi r squared, little r by the way, we get the electric field to be the volume charge density rho times the little radius, whatever we're looking at, which is going to be inside by the way, and over the epsilon naught. Right, now electric field outside of the sphere, where our little radius is going to be actually bigger than our actual radius, we have a similar equation, but this time we use a big radius for the formula of the volume of the sphere. And this simplifying gives us this equation for the electric field. Note that this is not the same as for a conductor. In a conductor, the charge is not located on the surface. The charge is located on the surface, but in insulator, the charge is inside because insulators don't conduct. So in a conductor inside, we had, as in class, we had the electric field to be 0, but here, the inside we have some electric field and outside we have some other electric field. So the reason I actually chose a spherical insulator is because now we can check this looking at the sphere as at a point charge. Knowing the formula of the electric field to be here, and rewriting our new formulas for electric field, we're going to check if that word is the same. And so I rewrote my rho in terms of the volume, and I got this electric field, and I did the same thing here, but simplifying, I got the exact same electric field as for point charge. Note that this is only for the electric field outside of the sphere, and this makes sense because if we have a point with a charge Q, electric field outside is going to be the same as for a sphere with charge Q, because it's still outside, it doesn't matter how big it is. But for the electric field inside the sphere is not going to be the same as the electric field of one single point. So that makes sense. And this is Anna Solovyov. Thank you.